Good evening. My name is Shreyas Jaykumar, and I am part of teams 3 and 4. And my teammates are Akshaya Rajkumar, Siddharth Satish Kumar, Hobo Yang, Yukun Lee, and A. Rohit Reddy. And the topic that we are working on is in-network computing for a final project. And this is just a quick introduction video that kind of sets the ball rolling from both a technical and from a business point of view. So I'm just gonna mute myself and let the video play, and then gonna start giving the introduction from a high level POV and talk about the problems and the solutions and etc. So yeah, here it goes. Okay, so as you could see, that's like a little video under 1 minute that kind of set the ball rolling. And yeah, so I'm just gonna give a introduction based on the video as you had already seen from a high level POV, right? So, right now, somewhere in America and probably in many parts of the world, and an elderly person, and to be honest, in this day and age, even like a middle-aged person is wearing like a small device on their chest, a heart monitor slash a Holter monitor, right? Now that little gadget is supposed to protect them. But the terrifying truth about that is when the heart starts doing something dangerous, the device sends the data all the way to a distant server in the cloud, waits for a response, and then fires an alert. And that basic round trip can take seconds. Now, when we compare like seconds to that of minutes or hours, doesn't seem a lot, right? But in case of like a cardiac event, an arrhythmia sort of event, and etc., that's basically the difference between life and death. And moreover, to top it all off, the battery drains so fast that the device needs constant charging. The patient's private health data travels across the internet where it could be breached. And also, um, uh, 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 sorry, lost my chain of thought. The yeah, the AI running inside that device is completely generic. It doesn't like on a generalized basis it might know, but on an individual from an individual point of view doesn't know like your body, your history, or your specific condition. So that's like the broken system that hundreds of millions of patients worldwide are depending on today. So the solution, so our team, including myself, is building something that changes all of this at a fundamental level. And as you could see from the first slide or the first part of the video, like that's the in-network computing for real-time multi-sensor health analytics. And the core idea behind that is simple but powerful, right? So instead of sending the entire health data to the cloud and then waiting, we bring the intelligence directly into the network, right where our sensors live, thereby making it an edge device. And our system intercepts health data on the wire before it ever touches a server and runs a kind of like a personalized AI model to meet our medical profile. Now here there is no sort of cloud dependency nor any sort of dangerous delays, and of course, since it's being locally processed, there isn't any sort of privacy risk, which is extremely important in this big data sort of day and age. And because that sensors are freed from doing any sort of heavy computation, the battery lasts dramatically longer. making continuous long-term monitoring finally viable. This isn't incremental improvement per se. It's like more of a new architecture, built on a custom hardware acceleration from FPGA to ASIC design, and wherein the overall industry is like sitting at somewhere between 80 to 100 billion dollars, which is kind of breakthrough, to be honest. So as we already touched base upon this, now comes like now we are going to dig deep into the uh, business dimensionalities pertaining to it. And now my teammate A. Rohit Reddy is going to talk about the potential and related market opportunities. Thank you.
Hey, hi everyone, I'm Rohit. So, as we mentioned in our last week presentation, so the total available market for this wearable devices and uh, the things related to measuring the sensor data, like capturing the sensor data, analyzing the data. So the total available market is $8 billion, and by 2030 this will reach to $180 billion. And there are three major players in this segment. One is iRhythm, the one other one is Oliver Grove and Heartbeam. So as you can see on the screen, like these three players approach the problem in different ways. So one use cloud, and the other use edge, and the other one uses like mix of both. So there are potential, like there are advantages and disadvantage for each of the approach. Like let's say if one has like more latency, the other solution has more power consumption. And yeah, so these are the like different drawbacks in each of these products. And coming to our product, where we do the computation on the network, not on the neither on the device nor on the cloud. So our solution is in between uh, both of both the edges. It's like a best of both the world. And yeah, so this is about uh, like market opportunity and where our product fits into the market and how a product is able to is different from the existing uh, products. Uh, and now Siddharth will tell you more about the like business opportunities and what we have explored from business point of view in this week. Over to you, Siddharth.
Hi, I'm Siddharth Satish Kumar. So I'll go over the unit economics, which is going to be a deep dive into the cost involved for our product. So for our product, we feel the main important costs are going to be around ASIC development and R&D, the packaging and testing of the ASIC chips, and then the hardware product development. All the hardware are revolving around the ASIC chip, for example, PCB, sensor, etc. And manufacturing costs for the product, and also the logistics for shipping and other certification and compliance we need, and other miscellaneous expenses should be there for a product. So we will have a deep dive from the concept to deployment costs involved in the product, and we'll also see our profit margins will be. So for ASIC development, most of the ASIC development is not required right now because we have done a lot of like our RTL stuff is already done. We just one-time cost involved in usual ASIC development is going to be the EDA tools, IP, and verification and validation. So these one-time costs are going to be mostly negligible to us right now, and mostly will be towards verification validation part we need to do for and check for all test conditions. And also another thing involved in ASIC development is going to be the tape out and fabrication. So we can we're going with a multi-project wafer and fabric. So and there will be cost from for that, and also for cost for fabrication per wafer. So it's preferable for us to go for a multi-project wafer as it's cheaper to use share silicon, and also with area limitations. So the cost fabrication for cost estimated cost for fabrication is going to be around $3,000 on the lower side, and If it cost will be around $10,000, and this is all gonna be it can't be done anyway. We can't like it's not unavoidable cost, and like unlike the for one time media costs, which are pretty much one time and it's pretty much done right now. So other important thing for us is gonna be packaging and testing of the chips. So after we are gonna have after we're done with the ASIC development, we're gonna have the chips for testing and packaging for further hardware deployment. We have to check the chip quality. So in this, most of the cost will be like one-time setup cost. For example, you're gonna have like big setup cost for testing, and usually the packaging cost is gonna be for a single chip is gonna be approximately $20 on average, and the setup cost testing setup will be around $10,000 and will be therefore and also be some per unit testing cost further involved. And also we need to have like a bring up and debugging both, which will cost around $5,000 for again for further testing and validation of our chips. So next is going to be the hardware product development. So for our chip, we need to have like crucially, it's going to be a sensor for our product. Mainly, sensor has to be of high quality for in order to do like proper uh, results and to test with our GPU and CPUs. So for that, we're gonna have like the high end sensors. So and also the PCB has to be pretty good enough so that we don't have any delay or in our like products. For that, we need high quality connections, which to have like high speed data connectivity. So for that, the main cost involved around PCB is going to be around $5,000, and for a high quality PCB, and also there's going to be a cost involved for power regulators, clocks, memory connectors, which is be around $50 per unit, according to our estimation. And the sensor we're going to go with will be a high quality sensor, which will again will be around $80 for the for top quality product like a Garmin and Garmin based heart rate sensors. And the casing and enclosing will be around $25 per year. Like 3D printed casing. So another important thing for a medical appliance is going to be certifications and the compliance we need for a product. So our product will, if you're going to be shipping into multiple countries, we need to follow all the certification compliances for every country we are going to ship into. For those, it will take some huge chunk of the amount, which is going to be like one time, but it will also be very the usually those certificates vary based upon our application and risk involved around the product. So from our research, the estimated cost will be around 75K to 200K, which is again one-time cost and license we require in order to operate. And other tangible costs will be around logistics, marketing, inventory management, and yield losses, which are unpredictable and could also be based upon the customer market. And the necessary costs can't be these costs are necessary and can't be discounted. And the rough estimate I've kept for this around $25,000 for 100 units, so around 250 per unit. Um, and for per unit manufacturing cost. So for a single unit, how much the cost is gonna be for ASIC? The whole complete ASIC package is gonna be around $50,000. Sorry, $50 per unit, with from fabrication to like final chip design. And then for the hardware development setup, it's gonna be around $100 per unit, including the sensors. So that and the whole mechanical structure, the other components are going to be around $30 per unit. Shipping and logistics will be around $10 per unit. So the total estimate cost will be around $190. And the current market price for the product will be around $250 to $300. So we are able to get a profit of around $60 to $110 per unit. So yeah, thank you.
One.
Okay, and I'm going to talk about some the power parts of our hardware. Like well currently because our hardware information is too old that the modern platform don't support this. So I'm using this Linux 10 version to estimate the power. And because our hardware is a little bit complicated, so if you want to estimate the whole systems, it will just crash. So what I'm estimating is just the top level of our hardware, and this is the result of our power. You could see that the static power is 0.1, and the dynamic power is 0.7, and the total is about 0.8. So it's pretty lower than the like for our competitive company, like they are using a big data center, and like a typical data center's power is about 10,000 watts. So it's not even comparable. And like for their device to detect the ECG signals, you could see that they need 90 seconds to download. So like so for our products, like we could implement this low power hardware inside it, and you could have a real-time output of your ECG data's predictions. Okay, that's all.
Okay, so thank you, Ikun and Shreyas, Das, and Rohit. I'm Hobo Yang as the risk manager in our group. My presentation here will be separated in two parts. And first part is about the business, and the another part is about technique. And for business part, what I did for risk is about I try to find the above products my teammate mentioned, and I try to say if anyone use it in our real life, and to say is it like people really want to buy it, and is there any still market for us to go into it? So actually, I did some research, and for example, I have a Apple Watch and I use it. I scrolled it down for the applications and I found a ECG detection applications and I use it to detect my ECG. And after I try it, I found a biggest disadvantages is that it cannot automatically analyze the heartbeat, and the thing is a watch, is a wristband. It didn't put on your nearby your heart or nearby your a very important place which can have a very good quality of signals for your heart, so that it cannot use for the medical. And it say if you are believe you are having a heart attack or medical emergency, call emergency service, which means it cannot believe it. But the truth is, why we need this? As the Apple, they already have a big market in our real world. So when somebody think like a normal guys who want to, okay, today I want to detect my ECG signal. Okay, it's very rare. But if someone want to say, okay, well, I want to say my heartbeat, my heart rate, what he will say? He definitely will say, okay, I'm going to buy an Apple Watch or something like a small watch to say my heartbeat or heart risk. And for maybe the apples they have their like ass, right? They are inside their ass. There may be a grandma or grandpa. They're wearing Apple Watch and they fall down and alert. It's quite impossible actually. But the truth is they already taking the big quantity of the market. So it's really hard for us to compete with them. So this is a really risk. We need to say it. So what I think is for our product, we cannot make it to be a B2C product. We have to make it to B2B, at least a very shallow level of the B2B. We can sell it to the hospital. We can sell it to some like other uh very expert like some expert company so that we can combine our technology into their product so that we can get our market. Why? because like for our product now, we only have a very small utilization to compute this system. So what's the biggest advantage we have? The first, customization, and the second, the lower bandwidth. So we need to take the most advantage of them. So what we can do, okay, what we can do? Like in the hospital, we have a lot of patients. We can also have a lot of sensor nodes, right? So for this sensor nodes, they can collect their data on themselves, and after that, they push this data to the cloud, and cloud do calculations. And after that, maybe your doctor can say that some patients have the symptom so that he will help them. Okay, I make a very simple animation to show this. Let me first take this hit. Okay, so for example, imagine like you are in a hospital, like everybody wearing Apple Watch to detect some symptom. Okay, so this part is Apple Watch style continuous upload. What is continuous upload? Like you are using a device that don't have any edge calculations. He directly uploads data to the cloud, and after that, the cloud do the calculations. But for our product, we are using Edge ECG platform. So we do the locally calculations. So when we have only 4 ECG devices in a hospital, we can see the bandwidth is 2 megabits per second and our is 0.8. Why is 0.8? Because we don't always push to the cloud, right? Only when we have find the alert. So the abnormal event rate is typical, which means it's a quite lower bit. We can make it to be lower so that we can have a lower bandwidth, but we can make it typical. Okay, so it's all good since we didn't get the threshold. But when we move this device number to get higher, we can say like the Apple Watch kind of continuous upload devices, the bandwidth goes faster, really faster than our Edge ECG platform. And when it goes higher and higher and higher, okay, he got a threshold. What happened in this kind of situations? Some patients, maybe we cannot only have 200 patients in a hospital, right? So those who also wear this bandwidth, wearing this wristband, they cannot upload their data to the cloud. So they cannot look, the doctor cannot look their symptom. So for our devices, it's still a lot of free spaces. Even though we make it to be high, we still have a lot of free. So this is what kind of advantages we want. And this is also the risk we need to avoid. And for another advantages I mentioned is customize, right? So I also made an animation for it. For example, we have this detection system, right? So we can have this kind of protocol on the doctor's computer. And for what kind of patients, we can set the still of it. Like for this patient, it's maybe let's as imagine like it's a PVC kind of patients. And we can set this one and apply this setting so that this device can only focus on this kind of symptom so that we will have a very customized module for it. It will not take a lot of the space of our device and it will use very little calculation utilization for our hardware. And that's also result a very low power consumption for our device, as you can say. Okay, so that's is my risk part for our business, and also as another risk, the risk part for the technique, I think is quite similar. The biggest problem is like we have a very low utilization, so that when we do this kind of put the module on the hardware, we need to find which kind of module we need to choose. Can it fit the patients? If there's a misunderstanding for the heartbeat signal, can we upload it to the patients, but not only just ignore it? So that's the second problem. And I will handle this to the Akshaya, and thank you. one.
In GPU core. So here we have a control unit here where I've added like two instructions for specific to the tensor unit. So one is called the tensor load and one is the tensor enable signal. So also here we have a so yeah, here we have including these signals here, which are the output signals. So yeah. So I've also added like two output recs for tensor unit in the control unit of the GPU. And coming to the GPU core, I've added these two signals, these two instructions, and the opcodes for it. And also here a condition where to monitor if the tensor enable is active and also the GPU is running. And also if the tensor has completed its operations, we have a valid signal here. So coming down to the EX stage, so coming down to the EX stage, I have define the signals here for the address T, valid, and the result. And also this is these addresses for the internal tensor memory. And I've instantiated the top level model here. So yeah, and also during the write back in the main stage, so depending upon the tensor instruction, so the tensor address location, we'll have the data stored there in the memory. So this is the top tensor code that we have already built. It consists of like an internal memory here and a register file. So yeah, we have data preparation, like the data pre-processing point of view. I worked on the notch filter and the Butterworth bandpass filter. So I'll show the code for this. So in the previous week, we had the prepare MITBHT, like the code for the data preparation and pre-processing. So in this, we've added like two functions for filtration, for signal filtering. So the main purpose of this is to take in the raw data of the ECG and then to apply like specific filters so that the processed data can be easily used to train the model that we have built. So the two filters that we have used is one is called the notch filter. So we have used this to filter out a specific signal of a specific frequency from the data set. So this is the 50 hertz electrical noise. So by applying this, we'll be able to filter out the specific 50 hertz from the data. And also these are the parameters that are present in the filter. So we have a notch frequency, the frequency to remove, Q factor, how narrow how wide or narrow the remote should be, the sampling frequency, and then the filter, like the applying filter phase. And we also have the Butterworth bandpass filter where the frequencies within the specific range are extracted. So, for example, in the ECG data consists of ECG signals which are from 0.5 hertz to 40 hertz. So, only these of the signals will be retained, and the others which are beyond the range will be removed, like will be smoothened. So, we have like the order of filtering, which we'll be using two for smooth filtering, and Yeah. So we have the output as like a SOS, second order section. So for large polynomials, this will be broken down into small filters. Yeah, so it's numerical stability. So that is shown here. We have the function for notch filter and button bandpass. And I've also done like a visualization of this filter like separately. So yeah, we have the same signals and then we will plot this side by side to see the difference when we are applying the filter. Yeah, so I'll be running the model here to the filter. So as you can see, this is the raw ECG signal that we have used from the data set. And we are able to remove the noise in the filter, like after the filtration process. Hi, this is Akshay. So I'll be talking about the novelty that we have come up with in this project. So, like the other models that are existing in the industry, they have like generic like machine learning models which taking data from the patient, and then they have like a generic model, a large model where they classify these type of symptoms. So in this, we have tried to build a patient-specific, like a customizable device wherein the patient's previous records can be inputted by the doctor. Like the doctor can suspect a series of symptoms which he can mention, and the device which is on the edge, like the custom GPU accelerator. It runs small models which the doctor selects, and based on this, the inference will be given. So instead of depending on the large model on the cloud, this can be done on the edge where the inference is quick, and also there is a reduction in the data transmission to the cloud. So based on this, we'll have the confidence levels where so are if the actual symptom is not what the doctor specified, like not in the range where the doctor specified, that will be sent to the cloud, and then it will be analyzed in the cloud. So most of the symptoms where the doctor suspects will be done on the edge AI. So this is what we are trying to attempt. And yeah, so this is one of the like the adaptive models where it is customized according to the patient's needs.